So, welcome to the afternoon session. I'm very, very happy to announce the talk by Ahmed Kebaier from Paris. Would be even nicer if Ahmed would be here, but it's a real pleasure to see him on the big Zoom screen here in this nice lecture hall. And Ahmed, who is an expert on stochastic numerics, and he will tell us about approximation of stochastic Voltera equations with kernels of completely monotone type. Ahmed, please go ahead.
Many thanks, Christian. Thank you also for Raoul and all the team, numeric team, stochastic numerics team at KAUST. Yes, that would be, I would love to come, but of course, for some lot of constraints this year, I can't do the travel. But I'm really happy to give this talk and thank you for this opportunity. So this is a joint work with Aurélien Alfonsi from École des Ponts at Paris, and in which we tried to improve first results that we got on approximation of stochastic Volterra equations when we use kernels of completely monotone types. So let me go through the talk. So at first I would present the general framework. Then in a second section, I would discuss the strong error when I approximate the kernel and give some results. And I will propose a kind of multi-factor approximation in this case. Then a third part is dedicated to discuss the problem of combining this approximation Volterra approximated equation, Volterra equations by Euler schemes, in order, of course, to have implementable schemes. And then we discuss also the strong error we get when we use kinds of Euler schemes. And then the last parts, and for the financial application, I will show you some results on the Rough Heston model case. So let me at first present the general model that I would handle in this case. So it is a stochastic, multidimensional stochastic Volterra equation here, and where you can see here two kinds of kernels, G1 and G2. So B and sigma are d-dimensional coefficients that for the whole talk they will be supposed to be globally Lipschitz continuous. And here we deal with general kernels that would have a matrix valued, so the kernels can be matrix valued here in this case with this L2 integrability condition on the kernels G1 and G2 in this case. So, and the additional assumption on our kernels is, of course, this completely monotone behavior. So in the multidimensional case, we would suppose that each of these two kernels can be rewritten as a Laplace transform of some positive real measure here, lambda, with some matrix here of weights that, of course, includes the row coefficients here. And we would suppose that the upper bound here that we should have on the norm of the matrix valued here kernels, the G bar here is of completely monotone type. That means its Laplace transform with respect to the lambda here, real measure, is finite for any t. So this is the general case we treat here. And of course, we have, of course, a particular interest in the case for the rough kernel, which of course now we know from since the very recent years it has a lot of applications in mathematical finance. And so the rough kernel case corresponds to a one-dimensional kernel that have this behavior. And of course, here for a power h minus 1/2 for h lying between 0 and 1/2. Of course, here you can see that this kernel is of complete monotone behavior and satisfies all the conditions I mentioned before, and of course the corresponding fractional measure here is given by the CH constant times the power of rho with minus h minus 1/2. So this is our general setting. And now we would try, of course, to define as a first part what we could suggest as a numerical approximation for this stochastic Volterra equation in terms of approximating the kernel. So, of course, the kernel, as you can see, it has, of course, a bad behavior around 0. So, of course, one has to be careful when trying to approximate such kinds of kernels. So let me at first show you a first generic result that would apply in the case where when we want to approximate kernels for such stochastic Volterra equation. So assume that you have candidates for approximating the kernels G1 and G2. Let us call them G1 hat and G12. So of course, this G1 hat and G12 will induce here a new stochastic Volterra equation that is called X hat. And this X hat, of course, will stand for your approximation for the original stochastic Volterra equation. Here, if we assume that each of the kernels have a second norm that behaves as a quadratic growth with a quadratic growth in terms of the original kernel, our original kernel defining the bow, then we are able to prove this kind of generic theorem that says the strong error between the original stochastic Volterra equation and then the approximation Volterra equation, where you plug in your candidates G1 hat and G12 for the approximation of the kernels, depends on this L2 bounds, where you see here appearing the L2 norm of the kernel approximation, on the kernel approximation that is between G hat and the G kernels. So this is one of the key results of this work that will lead us, of course, to define the schemes and study their strong error and asymptotic and even non-asymptotic behavior. So once we have this result, then we may assume, we tried here to propose a multi-factor approximation, of course, in the case of this multidimensional setting case. So here, for example, let me show you a first preliminary result. So as we assume that our kernels are of completely monotone types, this means that both of the two kernels can be, of course, written in terms of this kind of Laplace transform with respect to this real positive measure. And here, if we try to replace this lambda by a sum of components of Dirac component here, a combination of Dirac component with here positive weights and increasing sequence ρ1 to ρn, then the first observation is that if we replace such discrete, let's say, discrete kernel, if we plug it in the original stochastic Volterra equation 1, then we end up with a system, a Markovian system. Means that the process, the SVA process for this kind of kernel becomes completely Markovian. Why? Because it is a linear combination of x rho it and y rho it, where you can see here x and rho, x rho and y rho are solution to stochastic differential equations. So we recover the Markovian case, and this is one essential observation for the rest of the talk, because our approximation will be based on this kind, we call them the multi-factor approximation, when you replace your lambda measure here, positive lambda measure, by a discrete combination of Dirac weights. So, so this is about the first observation. And now, how can we apply this result for the case where if lambda, for example, is this kind of, let's say, this rough kernel case. So for this aim, we tried at first a kind of truncation step. So this truncation step means that you only consider you compute your kernel from 0 to k, because of course on a computer we need to truncate at some level, and here we fix the level of truncation with this constant k for the moment, and define the corresponding stochastic Voltera equation, where we plug instead here in the equation the truncated kernels instead of let's say the original ones. And then applying our first generic result, we are able to prove that in this case, the strong error here between the original stochastic Voltera equation and the truncated stochastic Voltera equation have an upper bound given by this r of k. And r of k is nothing but this double integral between k and plus infinity of this 1 over rho1 plus rho2 integrated with respect to the lambda measure here, lambda 0,1 and lambda 0,2. So the assumption here is that the convergence is finite. If it is the case, then the strong rate convergence is completely described by this upper bound r of k. So this is let's say the price or the error to pay if you have to truncate your kernel at some level k. Let's apply this for our case of interest, which is, of course, as I say, the particular case, the one-dimensional rough kernel, that is the lambda h is given by this kind of weights, rho to the power minus 8 minus 1/2. In this case, the strong error behaves like k to the power minus 2h. So if you take the norm, then this means that it behaves like k to the power minus h. So of course, this a kind of consequence of the truncation when applied for dimension 1. Okay. So once we reach this step, we would like to consider a given approximation now for the truncated kernel. So a second level of approximation, because still up to now, this truncated kernel, if you plug it here in this stochastic Voltera equation, of course, you, for the moment, at least for general case, you can't implement this on a computer. So the aim is we truncate and then we approximate with this kind. So we have this mentioned this observation that we will approximate the lambda measure here with a combination of Dirac measures. So the idea is what happened now if I approximate my truncated kernel here with a kind of combination of this Dirac measure. So then I go back here to my setting and define such approximation. For the moment, it's an arbitrary approximation, g hat k of g, of the truncated kernel approximation. And let's denote delta hat k is the difference between the two kernels. So for technical reason, we have to assume that the norm of this matrix valued kernels can have an upper bound given by delta bar t, where delta bar t is belongs to L2 of 0 capital T. And of course, we define a new scheme now where instead of the truncated kernel, we replace them by the approximation of this kernels that we call G1 hat K and G2 hat K. So let us recall now our two main assumptions up to this level. We have to assume that this upper bound R of k, this is the upper bound due to the truncation, let's say, step. We have to assume that this double integral is finite. So this stands for H1. And we have to assume that the difference between the truncated kernel and its approximation have this upper bound delta bar, where delta bar is supposed to satisfy this H2 assumption, means that we need this L2 integrability for the upper bound. So under this results, a first lemma here we can prove is that we have uniform upper bounds on the moments of our approximation scheme. So here, namely, we know that the second moment of our approximated scheme is finite. And as a consequence of this, we can apply our generic results in order to prove and to study, of course, the difference, the strong error between the truncated Voltera equation and the approximation of the truncated Voltera equation. In this case, this, of course, it's a straightforward application of our generic result that I showed you in the beginning of the talk. The upper bound mainly depends on the L2 error between the two kernels. So let me recall you, the delta hat kg is simply the difference between your kernel approximation and the truncated kernel here. So it depends on this upper bound. And now if we combine all the results, so recall that we already established an upper bound between the original stochastic Voltera equation and the truncated Voltera equation, and the upper bound we says that it depends on this R of k that we suppose to be finite. So combining these two results, we get finally the main result of this section that says the L2 error between the original stochastic Voltera equation and the approximation of the truncated version of the Voltera equation, this strong error behaves like R of k plus this L2 norm of the difference between the two kernels. So of course, this result applies even if you have multidimensional kernels in this case. So as I told you, the approximation for the truncated case is of course based on the first observation we had, because we want to have kind of approximation that have nice properties such as the Markovian properties. So for this aim, we want to approximate the positive lambda measure using a combination of Dirac measure. In this case, we define this discrete intervals, and we define these weights. And in this case, the g hat k would be, of course, the Laplace transform of the Dirac, of this combination of Dirac measure, where the alpha I, the weights here, are supposed to be the Lebesgue measure of this intervals. In this case, we apply our previous results, and for n large enough than this constant, we prove that the strong error in this case, if you, of course, have the choice, or if you take the choice to use a multi-factor approximation. So during the rest of the talk, from now on, this would stand or call this approximation a multi-factor when I use a combination of Dirac measure. So if you choose to use a multi-factor approximation, then the upper bound in this case, using this first truncation step and the multi-factor approximation then behaves like R of k plus k squared over n squared times the Lebesgue measure of the whole interval 0 of k. So of course, you can see here the impact of the behavior of your measure lambda on the rate of convergence. If we have to for example, to fix the number of weights or the number of multi-factor that I have to take in my numerical approximation. So clearly we have to choose a good balance between these two errors. And this corresponds to choose the n, the total number of weights that I have taken in my discrete Dirac sum, proportional to this constant that mainly depends on the Lebesgue measure of the interval 0k. So let us focus now on the particular case of the one-dimensional rough kernel case. So if I try to illustrate whether this approximation work or not. So as I said, so this is my Dirac combination for my weights, and I would consider the particular case of the rough kernel case. In this case, the strong error between the original stochastic Voltera equation and its multi-factor approximation have a strong error that behaves like k to the power minus 2h. And now the second term, in this case, for this particular lambda h, behaves like k to the power 3 minus 2h over n squared. So if we try to optimize this quantity, then you may choose n equal to k to the power 3/2, or equivalently k equal to n to the power 2/3. And finally, you end up with a strong error of order n to the power minus 2h times 2/3. So here, if you take the L2 norm, then the behavior is, the strong rate is 2/3 times h. So the h seems here to be a very strong character due to our approximation scheme, but the 2/3 is of course due to our approximation, and particularly the choice of the lambda weights here, the weights of my Dirac sum, and also the factors rho in. So in what follows, I will show you how one can improve this 2/3 rate and try to reach at least here, make this 2/3 convergent to 1. So as a naive approach, we used a Riemann approximation, but this is for the approximation of my kernel. So here, the naive approach is to use higher order rules, like the Simpson rules. Let's try it for the Simpson rule. In this case, as you can see here, this can be written. So here we decided to use a Riemann scheme up to some truncation order k to the power beta, and from k to the power beta to k, beta is lying between 0 and 1. Here we use the Simpson rule. So in this case, it seems optimal to choose. So for the Simpson rule, we have 3 weights, of course. This is a rule with 3 weights. And it seems that the optimal, after optimization calculation, the optimal weights are given by this constant you see here. And we are able to prove a first proposition here after a step of optimization, or several steps of optimizations. So the optimal beta to choose here is equal to 10 minus 6h divided by 13 minus 6h. And the truncation level should behave like n to the power 13 minus 6h divided by 15 minus 6h. If you choose, you take such a choice, then the final strong error behaves like, this 13 minus 6h divided by 15 minus 6h. So instead of the 2/3, of course, you can see that this is better than the 2/3 since we have a lower bound here. Whatever the h value here you take, whatever is the value, the lower bound for this is 5/6, which is still better than the 2/3 that we find using a Riemann sum. So based on this observation, why don't we go through really very high level or higher order schemes? In this case, we propose to use what we call the Newton-Cotes method. And then let me recall you, the Newton-Cotes methods is you approximate an integral of this type using G weights in this case. So we did the same thing as for the Simpson. For the interval between 0 and k to the power beta, beta is lying between 0 and 1, we keep our Riemann approximation. And from k beta to k, we use the Newton-Cotes rule with G weights. So of course, if you take G equal to, then you recover, in this case, the Simpson rule we just discussed above. So in this case, we proved the following. For such a choice of beta and such optimal choice of k, the strong error behaves like n to the power minus 2h times this weight. Okay, so this in this weight, as you can see, appears the G. So the G here stands for the number of weights you will consider in your Newton-Cotes approximation. Recall that for Simpson rule, G is simply equal to 2. So if we take G large enough, or G tends to infinity, of course, you can see that this power here is close to 1, and then we recover a strong rate of convergence of order 1 over n to the power h in this case. So this is the optimal rate that we can reach. So this is from a theoretical point of view, and of course this is an illustration. So we have a general result for the multidimensional kernel case, and we illustrate how it works and what are the let's say the rates of convergence in this case if we apply it in the if we apply this general method to the specific one-dimensional case, we would get this rate. So here we notice it in the one-dimensional setting here. There is an extra thing that we can do, is that the optimal choice for the weights can be improved if we consider rho of in is equal to this integral of rho lambda d rho divided by the weight of the interval of discretization. This is simply to kill the first order in the approximation, and we get still higher order. So for example, for the Simpson rule, if we here for the Riemann, for the Riemann rule here, if you do such a trick, you would recover the 4/5 rate instead of the 2/3. And for the Newton-Cotes optimized, of course, you would get this new rates. Of course, that when you take G tends to infinity, you still get 1 for this weight. But let's say here, for example, for G equal to, which corresponds to the Simpson rule, you would get here the 22 minus 4h divided by 25 minus 4h. And I don't know if you can see here a very naive computation at the right hand of here, at the right part of the slide. You can see that the lower bound is 20 divided by 23, which is larger than the 5/6 that we obtained before. So, okay, so this is an additional trick for the one-dimensional case that may improve the results for, let's say, fixed G here. But of course, when G tends to infinity, you still recover the optimal rate, which is, in this case, which is 1 over n to the power h. Now, let us look for the numerical results in this case. So for the numerical results, we focus on, it's just an illustration in this case. So it is in any case, let's say, it's just we want to illustrate whether or not this approximation works, because this approximation has the advantage to work in a multidimensional setting, and we try to see what are the rate that would be achieved for this approximation in the one-dimensional case. So for this, we choose the simple case. So xt is given by this Voltera integral that appears in the well-known Rough Bergomi model that we will see right after. And in this case, we tested the main four schemes we discussed before. So the first one is the very naive Riemann scheme. And if you remember well, we said that the rate of convergence depends on the 2/3 power here. The second one is the optimized Simpson rule. So with taking the rho I, it's still the Riemann, but with the optimized weight rho I n here, that kills the first orders. And then we move to to a power 4/5. And then the Simpson rule. So for the Simpson rule, we get this better power here rate of convergence. And the improved Simpson rule for this particular choice of the weights, we get this still better weight in this case. And we try to compare all of them and try to illustrate whether or not these rates we obtain here corresponds to correspond to the numerical results. Can we recover numerically these rates obtained here for the simple approximation of this stochastic Volterra integral? Okay, so let's have a look. So the quantity of interest that we would compute here is this L2 norm between, so we have four schemes, right? 1, 2, 3, 4, and I'm interested in the strong rate of convergence between all of the schemes and the original stochastic Volterra integral in this case. So here, if you write down your error, so we all agree that all of our approximations can be written in this form, right? Because it's a sum up to some n with some weight alpha I and exponential of some weights rho n. And of course, after that, the difference between a scheme and another is the alphas, how you choose the alphas and how you choose the rhos, okay? And based on this observation is that the xt as it's only given by this stochastic integral. Then if you compute the L2 norm, of course, if you compute the L2 norm, so this is our scheme here. All of our schemes can be written in these forms, and this is the limit, which is the stochastic Volterra equation. If you compute the L2 norm is explicit and is Gaussian random here. So this error is Gaussian random variable with explicit variance covariance matrix given by this expression, okay? So what this means that the error can be computed explicitly here. We don't even need any approximation to evaluate this L2 error. So we can really illustrate the rate of convergence that we proved theoretically and prove that if they are optimal or not. So this is what we get for the first tables. So in all the four cases we considered before, this L2 error behaves like constant times n to the power -2h times some factor gamma. And this gamma depends on the scheme you choose here between the first naive one, which based on the Riemann approximation, then you have the improved Riemann, then the Simpson and the improved Simpson rule. So let's have a look for the first one. So for the first one, here we used several values of h that are smaller than 1/2, and we reach here the h equal to 0.005. And of course here, the theoretical gamma is given here, and the approximated gamma that you can compute thanks to this quantities is given here. So as you can see, we have a good approximation. So the 2/3 seems optimal in this case. The 2/3 is the theoretical upper strong convergence rate, seems corresponding to the numerical results here. So the same thing happens for the 5/4 for the improved Riemann sum. Then I move to the third scheme, which is the Simpson rule. So this is the last line is for the last line is for the theoretical, of course, factor that we found in our proofs, and this is the numerical one. So it seems to correspond to this with only 16 weights in this case. And here the same thing for the improved Simpson. Okay, so this means that our theoretical results are confirmed by the numerical illustrations here. But if you look more closely for the last column, when you consider here a very small Hurst parameter h, as you can see, the error, the L2 error, is larger than 2. So, and this is, of course, from a practical point of view, this something is very, very annoying, and for pricing, for option pricing, of course, this is not sufficient for a given approximation. So this means that the constant that multiplies the strong rate of convergence are large, or enough large to make this error behaves in this way. So that's why we turned to a kind of systematic approximation. And for the systemic approximation, we try to go deeper in the truncation using a factor A here, and try to truncate piece by piece from k to 8 power n k. And here for each interval, we use one of the proposed schemes. So the aim here is that if we choose such approximation, as you can notice here, we can prove that it's a simple observation that the previous approximation kernels that I showed you before are smaller than the ones given by this deep truncation Ka, and which is still smaller than the rough kernel case. And we did a numerical trick in addition. So we multiply this kernel approximation by some xi here, and xi optimal is the one that, of course, will reduce the L2 error between the rough kernel and our kernel case. So it's kind of a lift for our kernel that improves significantly the numerical results, as you can see here. So in this case, we choose A equal 3 and we computed the L2 error. So we still have the rate of convergence. So this new scheme has no impact on the, of course, rate of convergence. It only improves the truncation constant. And of course, if you look now to the last case where you take a very small Hurst parameter, h close to 0.05, then you reach this errors, which is clearly better than the constant 2 we get right before. And as a final illustration, in this case, we applied this to the Rough Bergomi model. The Rough Bergomi model, you can see it's a stochastic volatility model, as you can see here, where appears the stochastic Voltera integral that we approximated right before. So you can conceive an approximation scheme for this Rough Bergomi model, and we simply here replace our kernel, which is t minus s power to the power h minus 1/2, with our systematic, the kernel that we get from the systematic approach, of course, and we tried to compare this to the original method by Christian and his co-authors from the paper from 2016 for a very small values of the Hurst parameter, 0.07, and this is a very challenging case, and a very small maturity here, 0.041. So as you can see here, the blue one stands for the original, let's say the benchmark given by the paper, in the paper of Christian and his co-authors, and our approximation is given by the red curve here. So we recover the smile for this range of strikes. We recover the smile convexity here for the Rough Bergomi model. So this is for the first part of this talk. Then let me move to the second part of the talk. But before, let me recall as a conclusion for this, recall our generic result. So our generic result says, if you have your Voltera equation and you have any approximation for the kernels you have, then you can use this L2 bounds. And of course, you are free to choose the approximation you have. And the better approximation on your kernel is, the better the approximation on the stochastic Voltera equation is too. So, and here it's worth noticing that in the dimension one for the rough kernel case, the interesting case, like a recent paper by Christian and Simon Brainis proved that using a Gaussian quadrature in this case, this strong error behaves like exponential, converges to zero in exponential way. So, so this means that the better the approximation you have, so here it's based on Gaussian quadrature, of course, you may recover a better approximation of the L2 error. Now, in the second part of the talk, I'm going to discuss what happened now if I combine Euler schemes for approximated, so for Voltera equation, for Voltera equation. So let us see. So in a recent paper, Richard and his co-authors proposed to use a classic Euler schemes to approximate the original stochastic Voltera equation that I showed you in the first of the talk. So here, as you can see, it's you freeze your. So here we are. So at time tk plus 1. So you consider a uniform grid, as you can see here. Tk is k times t over n. And you freeze your kernel for at each small interval, and you sum up to the order k here, and you freeze the coefficients like for the SD Euler scheme. So in this case, the main, you can see here, just looking to the scheme here, the main drawback of this Euler scheme, the first one is that it is, of course, not Markovian. So this is one clear observation, but the second observation here is you have to sum up to k here. The kernels, you have to sum them up to k. So this means that the time complexity here, or the computational cost, is proportional to n squared if you want to recover the value of your Voltera approximation to the maturity time, capital T. So in this case, we proved recently a second generic result that can be seen as a discrete equivalent of the first kernel generic result. In this case, for the above Euler scheme and for general, so I consider this Euler scheme, and I may assume replacing the G here by any arbitrary G1 and G2, and their approximation G1 hat and G1 2. So we prove a discrete equivalent of the first generic result one, and under the same assumptions, we prove that now if you replace the kernels here by some approximation G1 hat and G1 2, the strong error between the two Euler schemes with the original kernel and with the approximated kernel have an upper bound that, of course, mainly depends. So this sum, as you can see, replaces the integral between 0 and t that we had before in the continuous case, and it depends on this L2 discrete norm of. So the better is the approximation on your kernel, the better your approximation is, right? So if you see this first result. However, if we combine this result with the strong rate of convergence that obtained Richard and the co-authors, you may find the following results. So assume the condition of our generic result one holds, Then the strong error between the discrete Euler scheme where you replaced your kernel by an approximation kernel, G1 hat and G1 2, minus the Euler scheme, the original Euler scheme given by Richard and Cotes, the upper bound is given by this. So we have here T over n to the power 2 alpha. Alpha here stands for the regularity of your kernel. So in the case of the rough kernel, this alpha is exactly equal to h. And plus the L2 bounds, discrete upper bound we get. And here this mainly depends, of course, on the quality of your, let's say, approximation of the kernel. So in dimension 1, if I take G1 equal G2 equal to G lambda H, the rough kernel case, for H lying between 0 and 1/2, then the strong error between the discrete Euler approximation and the classic Euler approximation here behaves as follows. So you have T over n power 2h plus, so this comes from the results of Richard and Cotes, plus the upper bound we get from our second generic result here. Sorry, this one. Okay, so this is obvious. So let's try to comment this result from a practical point of view. So from practical point of view, and especially for the rough kernel case with small h, as you can see here, if you see these two upper bounds, there is no need to be much accurate on your kernel approximation, because of course of this upper bound that comes from the Euler scheme itself. So the Euler scheme without any approximation, if you take the real, let's say the true kernels from the very beginning, it's only because of this discrete Euler approximation you may pay this T over, sorry, the scale changed, sorry. So T over n power 2h. So there is no need to be much more accurate on your kernel approximation because of this upper bound coming from the nature of the Euler scheme here. Let's see an example. For maturity 1 and h equal to 0, 1, we may here, for example, using our, if let us assume that the error between the kernel approximation and the rough kernel is like 0.1, behaves like 0.1. This means that in order to achieve a 0.1 here error, a global error, you would need, of course, n minus 1h equal to 0.1, right? But this means that you would need n equal to 10 to the power 10. So, and it is really hard to achieve in practice, right? So in this case, so because of this, the nature of the Euler scheme and the discretization, so we don't need to be too much more precise in the kernel approximation in this case. But based on this observation, we propose an alternative Euler approximation. So in this Euler approximation, we will plug, so we take the Euler scheme by Richard and Cotes and plug in our multi-factor approximation. So and we get, finally, we get this couple, as you can see, of stochastic differential equations. So if we do so, we recover a Markovian setting for our approximation scheme, so which is still better, I mean, because of the nice property you may use when you have a Markovian approximation. So if we proceed for, let's call it now a multi-factor Euler scheme for the stochastic Voltera equation. So we propose this. You may notice something interesting in this case. So let me write the multi-factor Euler scheme in this case. It's given by this system of SDEs, stochastic differential equation here. So we propose, this is for the Voltera, and numerically we observed a significant improvement if you try to consider, of course, here on the centered schemes directly Euler schemes on this centered scheme. I mean, centered with respect to the initial point here. There are some improvements, significant improvements in numerics. So here is the centered scheme, and here equivalently, of course, the original scheme we have. So we have the couple for x hat, y hat, and the x hat n would be approximated by these two sums, and we recover a general Markovian case. But if you look quickly here, as you can see, I would say this remark right after. As you would see here, we sum our scheme not until capital N, but until little n, right? Okay, so the kernels are summed until little n, and so this is a big advantage compared to the original Euler scheme I showed you right before. So let's, to be more clear, let's write it for the simple one here. For this simple case, one-dimensional case, so the x hat, the centered scheme, would be written in this way. And as you can see, the sum here, you sum up to n, not up to capital N. Let me recall you that capital N is for the time discretization for the Euler scheme, and small n now is for the weights, the multifactor weights. And we have a first result here, a first theorem that let us take the original Euler scheme. So let me go back to the original Euler scheme we have here, that was the one introduced by Richard and Cotes, okay? So this is called xn, right? Now, this theorem says the following. If in that scheme, the Euler scheme, I replace the kernels G1 and G2 by this discrete combination of Dirac of exponential weights, then the Euler schemes xn, the one introduced by, the one introduced by Richard and Cotes, but replacing G1 and G2 by these two sums, coincides with our multifactor Euler scheme. So let me explain in different words this results. Means if you consider first the Euler scheme and then you approximate the kernels, this coincides with considering the multifactor approximation for the Volterra and then discretize, which was not clearly when you observe so separately both schemes. It's not so obvious. So there is some calculation to be done to see that both coincides. And this is good news. So this means that since they coincide, if I replace the kernels G1 and G2 by multifactors, then I would, of course, choose a multifactor approximation in this case, since the complexity here is simply n times capital N. So capital N is for the time discretization and n for the number of factors I have. And the complexity, of course, this is smaller than the n square that are obtained by Richard and Cotes. So to improve this, we even did a better approximation here. We noticed that when the weights are smaller to some here power, t over n of the power but beta, there is no need to choose weights, of course, that are smaller than the time step. This is the general idea. You don't need to consider weights, weights rho I, that gives you smaller errors than the original steps. So we define this n tilt with the stopping rules, and we plug in this stopping rule in our scheme. So now we sum up until n tilt, and this, of course, we obtain a better. So we have n tilt factor which is smaller than the original n factor, of course, we had before, and define this x tilde n scheme. It's the previous so the multifactor scheme, but improved using this type of stopping rules. And we proved, this means that the complexity now is n tilde times n, which is smaller than n times capital N, which is smaller than the n squares obtained by Richard and Cotes. So, and for the sake of simplicity, let us analyze the strong error for the case G1 equal G2. And it turns out in this case that both schemes x hat n and x tilde n are very close. The x hat n is the one without the rule truncation and x tilde n with the rule truncation, and the difference behaves like t over n to the power 2 beta. So in the practice, beta is gonna be equal to 1. So we applied this result, and of course, thanks to this result, we have the strong error in our schemes, thanks to the general results I showed you right before. Let me go back just to summarize this one. Okay, so we just ensure that this rate is of order 10 to the n2h, and this is enough, of course, to have a scheme that achieves the same error and with a less cost. This is the main idea. So let us illustrate this new schemes on the challenging Rough Heston model. And we here try to compare three methods. So the model, let me, this is the final results. So the model is the following. We consider the stochastic Rough Heston model. So the first one is the ST, the asset price, as you can see, and here the volatility is driven by a rough Cox-Ingersoll-Ross process, as you can see. Here you have the rough kernel. So we are interested here. YT stands for the log of the asset price, and of course we choose this parameters. The first scheme here is the classical Euler scheme, is the one proposed by Richard and co-authors. So in this scheme, as you can see, you sum up until capital N, okay? And you keep your original kernel here, the G lambda H. So this is the scheme. The complexity is of order n square. Now, our improved alternative schemes using the stopping rule here, you can see here, is given as follows. Is given by the Markovian and a Markovian approximation, of course. As you can see here, is for the log price is approximated as follows. And the volatility, we use the centered scheme approximation, the centered in terms of the starting point, of course. And here the trick is that you sum up, as it is a multi-factor approximation, you sum up to n tilde, which is of course smaller than n, which is of course smaller than capital N in practice. We also compare this to a very recent scheme proposed by Romer that is based on the hybrid idea scheme introduced by Bennett-Sen and co-authors. So he combined this hybrid approximation with the multi-factor, okay, with the multi-factor approximation for Euler, with Euler approximation, and he ends up with such a scheme. So you have, this is your Voltera equation, the volatility Voltera equation here. You have it here. Then you propose two types of approximation. The one where you keep your kernels here, and the one where you approximate your kernels with the multi-factor. So this is the hybrid method. And of course, you have to choose the kappa. And it turns out that from recommendation, numerical recommendation, that you can be found in the Bennett-Sen paper and Romer paper, kappa turns out to be equal 1. So in this case, we can easily write the schemes in this case. So the log, so still for the Rough Heston model, the log price is given by this dynamic, and the volatility satisfies this equation. And of course, there is the step where you compute the multi-factor, and where and the part between 0 and Tn, of course, you simulate exactly this part. So this is the hybrid multi-factor scheme proposed by Romer 2021. So we try to compare these three schemes here. And the first, we consider the same numerical parameters proposed by Richard and co-authors. So here you have V0, theta, and lambda, sigma, the correlation, and H is around 0, 1. Maturity is 1 and we start show it for European call option for the rough Heston model. It turns out in this case, we have using Fourier pricing technique, we have an approximated exact value, which turns to be equal to this constant here. And we use the systematic approach. The systematic approach is without the stopping rule on the n, so still with n factor. And also we use the stopping rule here with the n tilde factor. And here we gave numerical results for the L2 error between the original rough kernel and each approximation in this case. So if you consider the systematic case without any approximation here, multi-factor approximation, so of course this is for without any Euler approximation, I mean, but this is a multi-factor. So this is the error we get. And now if you consider the L2 error for the discrete, for the discrete scheme, then you get this two constant. So this is with n factor, and this is with the rule, stopping rule with n tilde factor. So it means that for the kernel approximation, this is the level we reach. And as I showed you before, we never, let's say, need larger than 10 to the minus 3 in numerical result because, of course, of the limitation of your, of course, the computer and the machine we use. So let me show you the results for the call option price. So as you can see, this is for the rough Heston model. At the left, we used the multi-factor scheme. At the middle is the Voltera Euler scheme. And at the right is the Romer multi-factor scheme. So at the left is our scheme here. As you can see, we can first compare the Euler scheme, the classical Euler scheme given by Richard and co-authors and our scheme. As you can see, the precision is quite similar. And even the values are quite similar since we proved that the two schemes coincide, right? When we use the same kernel. So here it's really very, very close here. We have the same error, but if you look to the time complexity, of course, we achieve the same error with less time complexity here. It's 583 seconds versus 3,136 seconds. Okay, so this is for the Euler scheme. So we have the same precision, but of course we are significantly faster than the Euler scheme. And compared to the multi-hybrid scheme, we noticed that the multi-hybrid scheme presents a bias that is also noticed in Romer simulations. As you can see here, the precision is not so. So here, of course, we compare to the true value, right? To the true value given by the Fourier transform. So the time is still reasonable for the multi-hybrid. However, the precision, of course, is not as good as for the classic Euler scheme and as for the multi-factor Euler scheme. And I finished the simulation showing you a case for which we don't have a benchmark price, look back option price, and the same things can be noticed if you compare between our multi-factor scheme, Euler scheme, and the classical Euler scheme. We have the same precision, and we improved here the time complexity in this case. So thank you very much.
Thank you very much for this nice talk. I think you can hear me now, right?
Yes.
Okay, because I think it didn't work before. Okay, are there any questions? Maybe one quick question, because actually we have to move on to the next point. What about weak errors? I mean,
Yes, so this is the challenging case. So yes, as we discussed before. So yes, we are working on this, but there are still challenges ahead for the stochastic Volterra equation. So it's not completely solved, but we hope with Aurélien, we hope, it's not of course sure because nothing is complete, but there are some maybe hints that and some intuition that may work, and we have to make them more rigorous.
All right, great. Are there questions from the audience? If not, then let's thank Ahmed again. And I'm sorry we had a few technical problems, I think, during this talk, but thank you, and it was very nice to have you here.
Thank you, Ahmed.
Thank you, Zona. Thank you, Howard.
Merci.
Thank you very much.
Have
a nice conference. Bye-bye.
Now